Hello students, welcome to lecture number 6, Grading a Building and Swale. So previously we talked about the methods of grading a level terrace using the 3 methods of cut, fill, and balanced. And then, just this passing class, we introduced the methods of grading a swale using provided parameters such as the centerline slope, the side slope, and the swale depth. And we explained in the grading of terrace exercise that was just the first step of creating a level surface for human activities, right? So next, we'll need to solve the drainage problem for that surface. So today, we put these two previous exercises together. That is, to combine grading for terrace and grading for a stand-alone swale to grading the building and swale together so that the swale protects the building from being flooded. So this is what a swale around a building can typically look like in terms of the contour pattern. And if you remember from the grading the terrace methods, the red contour lines here represent the balanced method for grading a terrace, right? Also, if you remember from the grading the swale method, a stand-alone swale has a V or U-shaped contour pattern, right? Now, if you look closely, can you see that the pattern we're trying to learn today is indeed a combination of these two? So the combination of a balanced terrace contours and two swales, one for each of the two sides of the building, is indeed the contour pattern we're trying to learn today. Now, we'll show you how to combine these two patterns in 10 steps. Now, the first step, same as any other landscape design project, is really to examine the site context, right? To look at the slope orientation, building orientation, solar orientation, and other site features. Now, in this example in the exercise, the building orientation is already given to you. In a professional career, that may or may not be the case. A more ideal situation will be for you, the landscape architect, to analyze the site and determine what the best orientation of the building will be, based on solar, vegetation, slope, and other site characteristics. In other situations, you may be working to address a predetermined building orientation, which, if not determined based on site analyses at the very beginning, can make it very challenging to work out the grading solution. Just an additional note there. So, in our example here, the most relevant site analysis will be to diagram how water moves through the site and how that affects the building to be built, right? So, the very first thing you need to do is look at the existing water flows, right? The runoff here flows from the high side to the low side of the site, in this case, from southeast to northwest. Now next, think about with the building on site, how would you like the water to flow? If we go back to the basics of the swale lecture, if you remember this section, two of the important points are that swale will always be on the high side of the structure and the ground surface immediately adjacent to the structure must slope away. So the proposed flow directions should include the flows away from all sides of the building and then flows along a swale that wraps around the high side of the building, right? To help you visualize the landform in 3D, here is a SketchUp model that shows in what directions we should direct water away from the pad. Now that we have the proposed water flow, The third step would be to set various elevations to start the grading process. Notice in this example and the exercise that the pad elevation is given to you, indicated by the FFE 22.30. FFE here stands for finished floor elevation, which we will explain in a minute. But just note here that FFE is set for you in this exercise. Later on, we'll ask you to set your own FFE based on what you think will be an appropriate elevation. Okay, in order to explain the concept of the FFE, I want to insert a little content here about the process of construction. So, in order to get a site prepped for a building like this one shown in the picture, the process is very much like creating a wood sculpture. So you first do rough carving, right, to shape the overall sculpture, and then you'd work on details such as noses and fingers, right? It is the same with site preparation. There are many steps for site preparations, but I'll only explain 3 key ones. So first, bulk excavation, aka rough grading. This is where the majority of earth moving and shaping take place. And you also need to excavate for the footings and foundations if you have any buildings or other structures, right? Once that is finished, once the footings and foundations are built, you need to backfill the excavations for structures. After that, fine grading is conducted to ensure that the earth forms and surfaces have been properly shaped and the surfaces is ready for the next phase. So what's the next phase? It's really to install the surfacing material. Okay? And the surfacing material can either be hard surfaces like pavements, it can also be soft surfaces like topsoil for vegetation. And you don't have to remember any of this at this point. Okay? The key thing is to understand there are multiple surfaces and associated elevations that are necessary to correctly guide the construction process. What we specify in this class are finished elevations for the last step here. Okay, the finished elevations can be either for hard surface, such as the FFE for the buildings, or soft surfaces such as the ground outside of the building. We'll definitely talk more about this later in the semester, but this is just enough content to help you understand the different elevations for a building. Okay, now back to these 2 finished elevations. In section view, the FFE is essentially the elevation that you're standing on inside a building. If a building has multiple floors, every floor will have an FFE. The second key finished elevation that we need to know is this one, the finished grade of the ground outside of the building. In particular, the finished grade for the corner, which is the highest point of the exterior ground to create the positive drainage we talked about in previous classes. Okay? Now, the relationship between the FFE and the corner elevations depend on the type of construction. We have here an example of a wood-framed building, indicated by frame construction here on the slide. This type is the type we use for this exercise. Okay? For wood-framed buildings, the elevation difference between FFE and the corners should fall within the range of 6 to 18 inches, meaning the corner elevation should be at least a minimum 0.5 feet, but at the maximum 1.5 feet below the FFE. Now, why this range of 6 to 18 inches difference? There are more reasons than you want to hear about. But most importantly, if this part of the building, as indicated by the green box here, is made by wood, this distance here, indicated by the purple line, prevents exterior water from easily entering the voids and joints between structures, and also allow the wooden wall and floor to breathe so that they don't decay as easily. Now, why not higher than 18 inches then? First, if you go too high, you'll have more of your building foundations exposed, right? And that is this part, as indicated by the red box here. And that exposed foundation will be subject to more potential damages, right? And second, 18 inches is about 3 steps high. If you go higher, it becomes increasingly difficult to get into your building. Of course, another reason is higher construction costs. Okay? But note that the 6 to 18 inches rule only applies here to the frame construction building. We'll talk about buildings with masonry walls later, and for those, this rule doesn't apply. Okay? So, to summarize the slide, two elevations are important: FFE and the exterior corner elevation. FFE should be 6 to 18 inches higher than the corner elevation for wood framed building. Okay? Now, with the 6 to 18 inches rule, we set the corner elevations for the pad. So, the acceptable range according to these calculations will be 20.80 feet to 21.80 feet. For ease of demonstration, we'll just set them exactly 1 foot below the FFE, okay, at 21.30 feet. Moving forward to the fourth step. Now remember, we have previously drafted out the proposed water flow. This blue swale line here is what we work on next. Okay? More specifically, first we focus on roughly locating the swale high point, HPS. How do we do that? We find the natural high point. Okay? Now what does that mean? So we know the southeast is the high side, while the northwest is the low side. So the green area here would be the high area adjacent to the building, right? And the HPS should be located somewhere in this high area next to the closest building corner, which is the southeast corner here. But where exactly? The key thing here is to pay attention to all the slope requirements on the sides of the building. For example, in order to make the spaces around the building usable, there could be a common slope requirement of less than 5%. Or you may see other requirement that the center line needs to be at least some distance away from the building. Requirements like that, right? The key here is to allow enough space between the building and the swale based on given slope or other requirements and the desired use of the exterior space. One key thing to note here is that this is an iterative process, just like every other design process. Try one location for HPS, and if it turns out it won't work, for instance, it will cause slope violations somewhere down the line, we'll try another one. It's definitely not set in stone with your first trial. Okay? Next, let's talk about how to set the LPS. For your first try, you can look at where the building corners are and locate them one contour below the edge of the corners. This way, the swale which ends at the LPS, will be able to get water past the building, right? So what does that mean? This 18 contour is the next contour below the northwest corner. And this 20 contour is the next contour just below the northeast corner. So you can roughly locate LPS in the areas as indicated by the purple circles here. Again, this is a trial and error process. It's not guaranteed that these locations will definitely work, but this is a good start. Okay? Last, I just want to reiterate rules about LPS that we went over during the Swale Basics lecture. So LPS is the point where the swale ends. Beyond this point, water returns to sheet flow. It is also the location where the swale returns to natural grade, which means the elevation of an LPS shouldn't be what the original elevation of this very location is. Okay? And that is what at grade here means. And this is a common rule that our students in the past forgot about. So here is just a handy summary of general principles that we just went through when locating your swale center line. Next, we move forward to set the elevation for the HPS. Now let's zoom in to the southeast corner that's the closest to the HPS. What we know here is the corner elevation is 21.30. We have already set a trial center line and the location of HPS, so we'll be able to measure the distance between the corner and the HPS, right? Let's say H here measures 10 feet in our example. In order to calculate the HPS elevation, we're trying to find V, so we're using the V equals to H multiplied by G equation, right? We're still missing the G here, aka the slope, to calculate V. Now, this is another variable that we'll need to set ourselves. In order to create positive drainage from the terrace to the HPS, we need to have a slope of at least 2%. Remember? Would higher slopes work to efficiently drain this area? Yes, but using 2% is a good start. It creates effective drainage and doesn't affect the use of that area, right? In addition, you will need to pay attention to other slope requirements that's given to you. For instance, in our exercises, there is a requirement for maximum 5% slope for the first 10 feet away from the building. Okay, so with all that said, let's set the slope as 2% as a start. Now back to the equation. V equals to H multiplied by G, and we plug in H equals to 10 feet and G equals to 0.02 here. We get V equals to 0.2 feet, and then HPS is corner elevation minus that V. So we have 21.10 for our HPS elevation. Now here, a common mistake is that sometimes students didn't realize that HPS should be lower than the corner to drain water away from the corner, right? So once you calculate V, the elevation change, remember that you need to subtract that from the corner instead of adding it to the corner elevation. Now the next step is to set LPS elevations. The basic principle is to interpolate between the two adjacent contours to find existing elevations at the two LPSs. Because this year we're doing this directly in CAD, the process can be a little different from when we were doing this on paper. The important thing here is to remember that even though we are in CAD and can be very precise all the time, When we are just testing a grading solution for the first time, we don't have to measure everything and calculate to 2 decimal places. Okay? We can still estimate just to test the trial elevations. Okay? Now, here are 2 different ways to set the LPSs. Let's look at the one on the east first, the easier case for this one. From previous slides, we have decided to locate this LPS in this area. For ease of testing and calculation, we could simply intentionally set LPS midway between the 19 and the 20 contours at the elevation of 19.50. And CAD makes it really easy to identify the location of that midpoint, 19.50. You could just draw a line between the 19 and 20 contours in this area, perpendicular to the 20 contour, and then use the divide function or simply snap to find the midpoint and call it 19.50. In other cases, you may say, I think we can locate the LPS a little higher so that water returns to sheet flow sooner, or you simply want to try something else and don't want to take the easiest route of finding the midpoint. That's totally fine too, right? You could try LPS equals to 17.70 as shown on the screen, or you could try 17.60, 80. The principle of calculating that location is exactly the same. So in this case of 17.70, you can again draw a line similar to the one we just drew. One way you could find where LPS equals to 17.70 in CAD is that you divide the line, this line that you just drew. The bottom right graph is just a demonstration of how to find that 0.7 tick mark. Okay, so you find the third tick mark downhill from the 18 contour here after dividing that line by 10. That's exactly your 17.70 spot. Of course, there are other ways to find the spot in CAD. We can definitely discuss that in class. Now that we have set the LPS elevations, our next step is to calculate the centerline slope. Since we're calculating slope, the equation to use is S equals to V over H multiplied by 100%. Here we find V by calculating differences between HPS and each LPS, and we measure H directly in CAD. So in our example, H measures 95 feet on the west and 64 feet on the east. Now, realize the number you get from CAD measurements will be precise with decimal points. Here we didn't include decimals just for ease of demonstration. So with H and V available now, you can calculate slope based on the above mentioned equation. So per our calculations, the west swell has a centerline slope of 3.58% and the east swell has a centerline slope of 2.50%. Now from these calculations, you know that your first trial of the centerline grading worked well, right? Because both centerline slopes fell within the 2 to 10% desired slope range.
Now the next step will be to locate the centerline contours. Okay, this is a process that we've gone through during previous classes, so I will be very brief here. You can start from either side of the swell. Okay, and the formula here to use to calculate H is H equals to V over G. You'll need to calculate at least 2 H's for each side of the swell. Take the east swell as an example. If you start from the LPS, to find the next whole number contour, which is the 20 contour, you calculate based on V equals to half foot, right? The differences between the LPS and the 20-foot elevation. So the H distance here to the next contour should be 20 feet. And basically, you measure 20 feet on CAD along the center line to find the 20-foot contour on the center line. And the second H that you need to calculate is the contour spacing. Basically, how far apart are the whole number of contours? And because the centerline slope is 2.50%, the contours should be 40 feet apart. So you measure 40 feet to find where the 21 feet elevation is on the center line. Now, if you would like to verify that your measurements are correct, you can definitely measure from the HPS to the 21 contour to see if the distance matches the 2.5% slope. And it will be the exact same process to locate centerline contours on the west swell. So we'll skip that part here for brevity.
Now the last two steps is basically to locate and draw all the contours. The key thing here is to pay attention to contour spacing on the sides. Be aware of what the required minimum spacing is on each side of the pad. For example, if the maximum side slope is 5:1, then the contours on the sides have to be at least 5 feet apart, right? You may want to use the offset tool in CAD again to generate guidelines to maintain the adequate distances between contours. Now let's zoom in again for a few things that we need to pay attention to. Notice that we're using the same requirement as exercise 6 to maintain maximum 5% slope for the first 10 feet away from the pad. So the first thing is how to find the first contour away from the pad. That is the 21 contour, right? Because all the edge elevations here are identical to the corner, which is 21.30, we use this set of calculations to find the distance h to the 21 contour. So we use h equals to v over h and plug in v equals to 0.30 and g equals to 0.05, and we get h equals to 6 feet. That means the first contour needs to be at least 6 feet away from the pad edge. So with that, we're able to maintain the 5% slope for the first 6 feet. What about the remaining 4 feet? In order to maintain 5% for that 4 feet, we need to have at least one additional spot at this exact location, 10 feet away from the building pad. Otherwise, the contractors won't be able to know that we have a flatter slope closer to the building, right? So here we use this set of calculations to find out the elevation of the added spot. And because we're calculating V in comparison to the edge of the pad, we use V equals to H multiplied by G and plug in H equals to 10 feet and G equals to 0.05, and we get V equals to 0.5 feet. So the elevation change from the pad edge to this spot should be 0.5 feet. And so the elevation of that spot is 20.80. And remember that this spot has to be marked in your grading plan for exercise 6 to be able to maintain 5% maximum slope for the entire 10 feet away from the building.
So the last step is really to double check all your slopes are falling within the required or desirable range, and polish your polylines and to label all necessary slopes. That is all for our lecture 6. Thank you for your attention. We'll see you in class. Thanks.